Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is Case Study and Field Experiences, Transformer Winding Resistance Measurement. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Samir Kulkarni, Applications Engineer. Also, to assist with the question and answer session, we will have joining us Dinesh Chajer, Technical Support Group Manager, and Daniel Carreño, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Samir.
Thanks, Mike. Good afternoon, everyone. Thanks for spending your afternoon with us. And today we will be looking at some case studies and field experiences associated with transformer winding resistance measurement. So let's get started. Let's go over the agenda real quick here. And we will start off with the purpose of this test. Why do we perform winding resistance measurements? And what are some of the common challenges we might face? And then we'll walk in straight to case studies. And while we are looking at these case studies, we will pay attention to the factors that affect measurement of winding resistance. So it'll help us understand all the factors that affect the measurement. And then we will end with summary. So let's understand the purpose. Why do we perform winding resistance? As said in the name, it is going to concentrate on your windings. So if you have situations where you have interturn shorts or loose connections in your winding, this test will be able to give you an indication of a potential issue. In addition to the windings, another important component is the tap changer. So with the tap changer, whether it's a de-energized tap changer or an on-load tap changer, you do not want to have a contact with high resistance. So you want to be able to diagnose and pick up such connections that could potentially have a high contact resistance. And specifically for on-load tap changers, which regulate with the transformer in service, it's very important that the continuity circuit be maintained. And any potential issue or any developing issue with this circuit needs to be diagnosed ahead of time to avoid equipment issues and even consequential failure. So in order to get a deeper understanding of this winding resistance, let's look at the equivalent circuit of the transformer. So here we have the circuit that we are interested in measuring the resistance of the winding of the primary and the secondary windings. Now this resistance is typically a low resistance value, and we are interested in the DC resistance of the winding. But you can see that in addition with the resistance, you also have an inductance that's connected in series with the winding. And this is because of the inductive nature and the construction of the winding. So when you're measuring the resistance, there's an added factor of the inductance that adds to your measurement. So for example, if you look at this equation at the bottom of your screen, you see that the voltage drop is not only going to have your resistive voltage drop, it's also going to have an inductive voltage drop that's driven by the inductance of the winding and the rate of change of current. Now, our main aim is to still measure the DC resistance. So one of our missions is to make sure that the inductive effect of the transformer winding is not part of our measurement. So ultimately, we are just interested in the DC resistance of the winding. So let's look at some challenges that we hear or we come across. So let's say you have a winding resistance measurement that never stabilizes. So your reading always jumps around. It never stops jumping around. Or you try to conduct a test and your test set unexpectedly trips when you're trying to start it. Or you're trying to measure the same winding on the transformer, but you always get a different reading. So let's try and understand what factors play a role in such challenges. So with that, we will look at our first case study. So this first case study deals with selecting the proper test current magnitude when you perform the test. If you review industry standards such as NETA and IEEE, you will see recommendations that say that the test current that should be used should not go beyond 15%. And the key reason for that is if you use a test current value greater than 15%, that could potentially heat up your transformer winding. And as your transformer winding heats up, the resistance is going to change. So your whole effort of measuring the resistance of the winding is futile because now the quantity you are trying to measure keeps changing. So that's why we should maintain a test current of less than 15% of the rated winding current. So as I said, we are going to look at the factors that affect those measurements. So let's look at winding inductance. So because of the construction and the nature of the transformer winding, it will not allow, because of the inductive nature, it will not allow a change in current. So if you're trying to measure a transformer winding and you want to inject 10 amps, the inductive nature of the winding will not allow you to immediately have a step change in the amount of current that's flowing through the winding. So how does the transformer winding counteract that change in current? So what it does is it generates a voltage across itself. And now when you're only interested to measure the resistive voltage drop, you also have an inductive voltage drop, as you can see at the bottom of your screen here. And if you have transformer windings that have a higher current rating and a higher power rating, naturally such windings could take longer to give you a stable winding resistance measurement. So our first case study, let's look at the transformer that we were reviewing. So in this transformer, it had a high voltage winding of 13.8 kV with a nominal rated current of 156.89 amps. On the low voltage side, it had a voltage rating of 2.4 kV with a nominal current of 902.11 amps. It had an overall rating of 3.75 MVA. It had a vector group of DD0. By that, it means it was a delta configured winding on the primary and a delta configured winding on the secondary as well. It had a De-Energize tap changer that had 5 taps, and it did not have an on-load tap changer. So we measured the winding resistance of this transformer on the low voltage side. So we started off with the X1, X2 measurement. Initially, we used a current of 10 amps, and based on that, we got a measurement of 5.917 milliohms. And it took about 101 seconds to stabilize, so about a minute and 40 seconds. So after we completed that measurement, we repeated the measurement with a slightly higher current. So we jumped up to 25 amps, and we measured a very consistent resistance measurement, but it is slightly different, but very close to what we got before. So we got a value of 5.926 milliohms, and it took about 95 seconds to stabilize. So you can see that there was a slight drop in the amount of time it took for the reading to stabilize, but it wasn't a lot. It was about 6 seconds. Now we did this exercise for a third time. In this case, we selected an even higher current of about 50 amps, and we measured almost identical resistance values of 5.926 milliohms again. But you can see that there was a significant change in the amount of time it took to stabilize the reading. So it went on further from 95 seconds to about 80 seconds. So when you compare that 80-second value with the very first measurement of 101 seconds, where we used 10 amps, you can see that the time it took dropped down by 21 seconds. And it's important here to realize that if you look at the percentage rated column here to the left-hand side of your screen, the percentage is still within 15%. You can see even with a 50 amp test current, the percentage rated current was still 5.54. So that's why it's very important to make sure that you are within the 15% recommended test current. And of course, when we were making these measurements, every time we used a different test current, we demagnetized the transformer. So we can get true measurements. So now, what were our observations? So you can see that a higher current provided early current stabilization, and that happens because of a higher test current, you're reducing the inductive effect of the winding when you're making these measurement, and that's why you get early current stabilization. And that can translate into time savings. Whether you are performing maintenance testing or even commissioning testing, you can save time while you're making through measurements. We saw that we saved almost 21 seconds for one measurement. So consider yourself at a commissioning test of a transformer that has 5 taps on the De-Energize tap changer and say 33 taps on the Oltc, or even if you have a bank of transformers, say you have 3 single phase transformers that you are commissioning testing or even maintenance testing for that matter, you can save time by selecting the proper current test current magnitude. And again, it's very important that we stay within 15% of the rated winding current. Now let's move on to our second case study. This case study is going to talk about the instrument open circuit voltage, also known as the compliance voltage. So this is pertaining to the test instrument that you would be using to make the winding resistance measurement. So the fact about open circuit voltage is that it plays a crucial role in measuring winding resistance. So while we are injecting current into the transformer winding, we are also subjecting the transformer core to saturation. So we want to saturate the transformer core in order to get the transformer winding resistance measurement. So the transformer core saturation depends on voltage and time. As you can see in this equation here, the flux that it takes to saturate the transformer core is dependent on the voltage and the time for which that voltage is applied. So because of this relation, it is intuitive that if you modulate the value of the voltage you use or the time for which you apply it, you can get a different setup for the flux. By that I mean is to establish the same saturation flux in the transformer core. If you use a higher magnitude of voltage, you will likely reach saturation in a shorter amount of time and vice versa. So let's look at that. So in this example, we had a transformer that had a high voltage rating of about 68.8 kV. It had a nominal current rating of 209.79 amps. On the low voltage side, it had a 13.09 kV voltage rating and nominal current of 1102.66 amps. It had an overall rating of 25 MVA, a vector configuration of delta Y and 1. So it was delta configured on the primary side and Y configured with a neutral on the secondary side. It had a de-energized tap changer with 5 taps and an on-load tap changer with 33 taps. So in this case, we measured winding resistance, of course. So we started off with a value of 40 volts DC on the open circuit voltage. And we used a test current of 10 amps. And we measured the resistance of each phase of the transformer on the low side. So if you look at the first measurement, X1 through XO, it took us about 1 minute and 7 seconds to get a resistance value of 13.86 milliohms. The same exercise on the Bravo phase, we had measured about 13.88 milliohms and it took about 35 seconds. And the third phase, we measured 13.95 milliohms and it took about 1 minute and 2 seconds to get a stable reading. Now we repeated these measurements after demagnetization with a higher open circuit voltage. We used 67 volts DC in order to make the measurement. However, we kept the test current constant. It was still at 10 amps. But you can see that we measured almost similar resistances, but with a significant drop in the time it took for the measurement to stabilize. So for the A phase, that is the X1 through XO measurement, we measured 13.84 milliohms in 38 seconds. For the B phase, we measured 13.87 milliohms in 21 seconds. And for the C phase, we measured 13.94 milliohms in 33 seconds. So you can see that there's a dramatic shift, especially in the A and the C phase, on how long it took to measure the same resistance with the same test current but now using a higher open circuit voltage. So what were our observations? We obviously saw that a higher open circuit voltage required less time to saturate the transformer core, and this translated into a faster stability of the reading. Now, let's move on to case study number 3. So this case deals with dual winding injection. And let's try and understand the concept of dual winding injection. In this method, we test two windings on the same phase. So let's say you're testing the Bravo phase or the B phase. So you will be testing the high voltage and the low voltage winding of the transformer. So this method utilizes the turns ratio of the transformer and the ampere turns to achieve faster core saturation. So now let's say you injected about 10 amps on your low voltage winding. So the ampere turns, if the low voltage winding, say for example, had 100 turns, so you injected 10 amps through 100 turns. Now by using the dual winding technique, you circulate the same amount of current through the high voltage winding itself, which is going to have a higher number of turns, let's say 1,000 turns. So you can see that turns product is now much higher. And what the consequence is that you are achieving core saturation in a more quicker manner with the dual winding injection technique. And in this technique, windings of the opposite polarity are connected together. And that is to maintain the direction of current in the transformer and such that the flux that's generated is still the same. As you can see on the right side of your screen, you can see that the injected current, once it comes out of one winding, is connected to the other winding and is again circulated through the transformer. And this is done by making sure that the direction of flux still stays the same. And this method has been found more effective in transformers that have a turns ratio of up to 10. And what we saw in transformers with higher ratios was that the difference in the nominal current of the high voltage and the low voltage winding was far apart, which did not give us the results that we expected. So for transformers that have a turns ratio of up to 10, the dual winding injection technique can be effective to make winding resistance measurements. Now, another important aspect of the dual winding injection technique is when you are measuring delta windings. So with delta windings, we know that there are two other phases that are part of the connection of the delta. And because of that, the two other windings can represent closed loop inductors when you're trying to make a measurement. And because of this delta connection, the current that circulates will also be distributed in the untested phases, and it will load the measurement of the phase you're trying to measure. And this eventually results in longer times for stabilizing of the current and for getting a measurement. So on the left side of your screen, I have two graphics. One is of a delta winding. So let's consider we are testing phase A. And I've put a quick graph of the current in that phase, the resistance that is measured, and the voltage that's applied across that phase over time. So this phenomenon is kind of, I've put it in 4 stages. So the first stage, you're applying voltage to the phase under test. So let's say phase A in this case. So the voltage on that phase is going to be high. And at the same time, the total inductance of the circuit is going to have the Bravo and the Charlie phases, the B and C phases together. But however, because you're testing the A phase, the current in that phase is higher. Now we enter stage 2. As your current goes higher in the A phase gets saturated, and then your current goes to the set maximum, and the voltage across that phase will drop. Now, it's important to understand that here only the A phase is getting saturated. However, you have a parallel combination of the B and the C phases that is still not saturated. Now we enter stage 3. Now, in this stage, the current in the parallel windings, the B and the C winding, will slowly go up. And this change in current is slow because the voltage that you applied is now lesser than the previous open circuit voltage that you applied on the terminals. And because of this, the current rises slowly. So initially, you might seem that this reading is steady, but it's really not. And stabilizing of that reading can take a long time. And then finally, we enter stage 4. In stage 4, the phase that you are testing, so A phase in this case, is still saturated. And then now, in addition to that, the other two phases, the B and the C phase, also get saturated. And what happens now is that the current and voltage stabilize, and then the resultant resistance that you measure is a combination of the B and the C phase resistances in parallel with the A phase. So now let's look at the example associated with dual winding injection. So in this example, we had a transformer that had a high voltage winding of about 13,800 volts and a rated current of 157 amps. It had a low voltage winding of about 2400 volts and 902 amps nominal current. It had a 3750 kVA rating, a vector configuration of DD0, so that is delta on the primary and delta on the secondary. It had a DETC with 5 taps and no OLTC. So we measured winding resistance on this transformer as well. And we started off with using single injection techniques where you just measure one phase at a time. And on the high side, or on the primary side, we started with a magnitude of 10 amps and we measured about 257.2 milliohms of resistance. And it took about 60 seconds to stabilize. Now, we measured the low resistance as well, the low voltage resistance, and we measured about 5.917 milliohms, and it took about 100 seconds to stabilize. Now, we use the dual winding technique to perform the same measurements. And after performing that, we saw that with the same magnitude of test current, we got two readings which were fairly close to our original readings, and both readings were obtained in a matter of 72 seconds. So the time it took to stabilize the reading was 72 seconds. So you can see that there's an immediate change of 89 seconds. And not only that, you're getting two measurements in place of one. So the total time it took for both these readings was about 161 seconds, and that dropped down to 72. So what were our observations for dual winding injection? First is we get two measurements simultaneously. And because of the nature of these connections and how we are achieving core saturation, it reduces the settling time of the reading. And this will lead to quick measurements and the time it takes to stabilize those measurements. So as we saw that for single injection readings, it took us a total of about 161 seconds. But those same readings were obtained in just a matter of 72 seconds when using the dual injection readings. Now let's move on to our next case study. This case study deals with two-phase measurements. In that, let's understand the concept of two-phase measurements. So in this case, we have two windings that are also measured, but they're on the same voltage side of the transformer. So if you're testing the A phase and the B phase on the same, for example, high voltage side of the transformer. So in this method, current is injected through two phases. So you can see here, the positive polarity of your current is coming through H1. It's flowing from H1 to H3, and then it's returning back through its negative back to the test set. So you can see that current is circulated from the A phase and the C phase for this example. And once current is passed, the voltage drop that's generated in the winding is measured from phase to neutral. Now, it goes without saying that windings and winding configurations that have a neutral available can be used to make these measurements. So a neutral must be available when you're making two-phase measurements. And as far as the third winding is concerned, a per phase measurement can be made. So let's look at an example for this case when we made two-phase measurements. So this transformer, it had 68,800 volts as its high voltage winding for voltage and 210 amps as its rated current. On the low voltage side, it had about 13,000 volts and 1103 amps. It had a rating of 25 MVA, a vector configuration of DYN1 That means it's a delta configured on the primary side and a Y configured neutral on the secondary side. It had a de-energized tap changer with 5 taps and an on-load tap changer with 33 taps. So again, we measured the winding resistance of the transformer. First, we used the per phase technique. So in per phase, we used a test current of 10 amps and we measured 3 winding resistance measurements. So the first one we got was 13.84 milliohms, and the B phase measured at 13.87 milliohms, whereas the C phase gave us a value of 13.94 milliohms. And right off the bat, the winding difference percentages were calculated, and you can see that this value is at about 0.72%, which is well within the 2% industry criteria. Now, what we did was we repeated the exercise with two-phase measurements. So in this case, we used the A and C phases to test simultaneously with the same amount of test current of 10 amps. But in what we saw was the resistance for the A phase was slightly different. We measured a slightly lower resistance, and this change was about 70 microohms. The B phase, however, came out to be exact same because we used the per phase measurement technique. On the C phase, again, we saw a drop in the amount of resistance we measured, and this drop was about 90 microohms. Overall, though, the final diagnosis was not different. We were still within the 2% criteria, although now the percentage deviation was lesser. So let's look at the observations in this case. So as far as observations go, we realized that there was a difference of about 70 to 90 microohms when measurements were made on a per phase basis or when they were made in a two-phase basis. So we saw a difference in the magnitude of measured resistance. Now this was because in the two-phase measurements, the neutral bushing does not see any current flow. So when you look at the measurement that we discussed in the beginning of this case study, we saw that current flows from your H1 winding through your H3 terminal. So it flows through your A phase and the C phase. So current never flows through the HO bushing. And because of that, the voltage drop and the resistance path is not accounted for. And however, we saw that in spite of having that difference, the effect was not very significant when the resistance range for the winding was between 10 to 15 milliohms. So we saw, as you can see on the right of your screen, that the winding difference percentages were not significant as we used two different measurement techniques. Now let's look at a case where we use two-phase measurements, but now we see a much different picture. So in this case, we had a transformer that had a high voltage rating of 44 kilovolts and a nominal current rating of 98.41 amps. The low voltage winding was rated at 4.16 kV and a current rating of 1041 amps approximately. It was rated at 7.5 MVA and it has a vector configuration of DY11. So it's delta configured on the primary side and a Y with a neutral on the secondary side. And it had a de-energized tap changer with 5 taps and an on-load tap changer with 33 taps. So we measured the winding resistance of the low voltage side. And what we did was we used the A and the C phases to make those simultaneous two-phase measurements. And for the B phase, we measured per phase basis on a per phase basis. And we took those measurements across 4 taps. As you can see on the left-hand side of your screen, this is the graph of the resistances that we plotted. And based on that, you can see that there is a difference between the orange trace that's up top and the gray and the blue traces, which are fairly close to each other. But both the gray and the blue traces are slightly separated from the orange trace. And if you look at the table on the right, the percentage differences are again out of specification. They are beyond the 2% value that industry standards recommend. So this is a case where measuring using the two-phase technique gave you readings that were out of specification. Now let's try to understand what that means. So our observations was again that there was no current flow in the neutral bushing. That's why the voltage drop associated with that connection was not part of the measurements for the A and the C phases. As you can see, for XO through X1 and XO through X3, the neutral bushing drop, voltage drop is not considered. And as you can see in the diagram to the bottom of your screen, that the HO terminal is used to just measure the voltage. There is no actual current flow. And what we concluded was that we use the B phase to get our references on what that resistance path would look like through your HO connection to your HO bushing. And we realized that it was about 150 microohms. That was the path resistance for that. And once we realized that, we added 150 microohms to the resistance values for the A phase and the C phase. And based on that, you can see on the right hand side of your screen that both those resistance values now are much closer to each other. So basically, all three resistances are measuring very close to each other. And when we tabulated that information and we calculated the winding differences, all the differences were within specification. So they were within the 2% industry criteria. So here's an example of how applying the right technique and understanding the right winding configuration helped you get an out of spec reading within spec. Now let's move to the next case study, which is case study number 5, and that will look at some tap changer contacts. So in this situation, we had a transformer with a high voltage winding of 345 kV and a rated current of 278 amps, and a low voltage winding of 34.5 kV with a rated current of 2778 amps. It was rated at about 166 MVA. We do not have vector configuration information, but we do know that it had a high voltage tap changer with 33 taps. And this high voltage tap changer had a reversing switch. So this is the diagram, or this is the nameplate of the transformer. So let me zoom in real quick and show you guys. You have the 345 kV as your nominal tap, and then you have successive taps that go higher in voltage as you go from 16 from your neutral to 16 rise, and then your voltages drop as you go from neutral to 16 lower. And in addition to that, you also have your tap selector contacts that go from 1 through K as you go from 16 raised to neutral. And then of course you have your reversing switch connects. Also to the right hand side, you can see a report of the winding resistance measurements for the B phase and the C phase as we moved through the tap changer from the 12 raise position to the 13 lower position. And let's look at something that's interesting with this report. When you look at this test, you can see that there are a couple of places where there was no data that was recorded. So for the B phase, you had a 6 raise position that had no resistance information. And when the make before break functionality was checked, there was no verdict of that test at all. The same behavior is seen on the 10 lower position as well. There is no data in the table for that position on the B phase, and there is no verdict of the make before break test either. So we were intrigued by this case, and we ended up plotting the resistance values. And obviously, as expected, we didn't have any value for the 6 raise position at all, or even the 10 lower. But you can see that overall, the behavior, as you would see in many cases of a V curve, was consistent, and most of the readings across both the phases were fairly close, but of course with this big anomaly of not having any readings. And if you look at a couple of slides ago, if you look at the nameplate, and I'm going to zoom in real quick again. So we had issues with the 6 raise and the 10 lower position. So if you look at the tap selector contacts here, for 6 raise, you had used the tap selector contact 11. And for the 10 lower, it was the same tap selector contact at 11 as well. So now let's look at the data with this additional information. We see that both positions use tap selector contact 11. So based on that, we decided that an internal inspection should be performed, and it was recommended to be done. And once that was done, we found that the contacts associated with number 11 had burnt. So this is a classic example of using winding resistance to detect potential issues with your transformer. And because of the fact that we were suspecting an open circuit, that was proven by the internal inspection. Now, let's move on to our next case study. This particular case study deals with field experiences that we came across while testing an auto transformer. So, this transformer had a high voltage rating of 345 kV with a rated current of 1338 amps and a low voltage winding rating with 143 kilovolts and 3229 amps. It also had a tertiary winding which was at a reduced rating of 100 MVA. So it had a 23 kV voltage rating and about 2500 amps as its nominal current rating. However, the overall rating of the transformer was significant. It was 800 MVA. It was of shelf type construction. And as far as vector configurations go, it was Y grounded on the high voltage side, Y grounded on the low voltage side as well, with a delta tertiary winding. This transformer also had a high voltage tap changer that had 33 taps. So this is the transformer picture and the nameplate. So if I can zoom in, you can see that it had a high voltage tap changer with 345 kV nominal, and it had, a tap selector and reversing switch. And you can see the YN1 configuration for the vectors, and you can see the terminal arrangement for the bushings. So considering the rating of this transformer, we had some interesting thought processes that we had to put together while testing for winding resistance. So some of the factors we considered was the transformer size, the transformer rating that was involved. This was a pretty high rated transformer. And in addition to that, in order to make effective connections to all of our windings, we needed to know the bushing placement for the transformer, which we just saw in the previous slide. And in addition to that, we also wanted to make sure that we were using the right leads and we were able to reach all the proper locations on the transformer. So in this case, we ended up using the maximum lead length for our test set, and that was about 18 meters. In spite of that, we were not successful the first time while we tried to connect. This was because of how the arrangement of the bushings was. And you can see here on the right hand side of your screen at the bottom, you have the high side bushings on one side, the tertiary windings on the right hand side, and then the low voltage on the opposite side. So in order to make good connections, we had to place the transformer test set right below the radiators right here. If you can see on the left side of your screen where I'm pointing at, that's where we had to keep our test set. And then we had to use a bucket truck in order to get the leads up to our bushings to make connections. So not only did we have to use the longest leads, we had to use a bucket truck to make those connections. So having these discussions beforehand will help you prioritize your work plan and make you more efficient in testing. So as far as testing for the transformer goes, we selected a test current of about 50 amps based on the rating of the high voltage side. And here's what we found. So in our observations, we found that the resistance values for the high voltage winding took almost 15 minutes to stabilize. So on the right side of your screen, you'll see the graph of the B and the C phases for their resistance. So you can see that the resistance values do stabilize, but it took as long as 15 minutes for that value to give us a final stabilized value. Now you can see the final values was 45.19 milliohms and 45.21 milliohms, which were fairly consistent and close to each other. But here's the discussion that we had in the beginning, that based on the rating of the transformer, it can take a significant amount of time for winding resistance measurements to stabilize. So it's important that we keep in mind the design and the rating of the transformer so that we can better predict the amount of time and challenges that we can face while measuring winding resistance. And after we made those measurements, even when we were discharging the winding, it took us about 45 seconds to discharge each winding. So these are all the thought processes that should be discussed when we are getting ready to test transformers. After we made winding resistance measurements, we also checked for the make before break condition of the tap changer. And while we were changing taps, we monitored the make before break circuit. And once we landed on a particular tap, we waited for a minute for the readings to stabilize. And what we saw was that the readings were in close proximity of each other, and the transformer passed on all tap positions for resistance. So if you look at the right side of your screen here, you can see that this may not be a very typical graph for how resistance varies with tap positions. Typically, we can see a V curve for a resistive type tap changer, but in spite of having an irregular curve, it's important here to understand that the values for the resistances haven't changed significantly. You can see that the minimum value, let's be conservative here and say it was 45.15 milliohms, and the maximum value was 45.4 milliohms. So you can see there's not a lot of variation, about 0.25 milliohms, I would say, in the resistance value across all 17 taps. So the point here I would like to present is that even if the traces for resistance versus tap positions may not be typical like a V curve, it's important that you review the magnitudes of resistances as well, which will give you a better understanding and better grasp over test results. Now, let's move on to our last case study. This case study will deal with complementary testing. And by that, what I mean is how can we use information from other tests as well and then correlate that with winding resistance measurements to get a full assessment of our transformer winding. So you know that there are several other transformer testing techniques for windings where you have turns ratio, we have dissolved gas analysis for oil filled transformers, then of course you have sweep frequency response analysis, also known as SFRA, and excitation current. So all these are complementary tests that are performed in addition to winding resistance to gain a better understanding of the status of your transformer winding. So let's understand how that is done. So for this example, we had a transformer that was rated at 22 kV on the high voltage side. It had a low voltage winding at 4.16 kV. And although we were not able to get a lot of detailed information as far as the rating and the taps, but we know that it had a delta Y vector configuration. So let's understand the background for this transformer. So when we performed winding resistance, it was shown that the resistance on the low voltage B phase was deviating by about 17% from its counterpart phases, that is from the A and the C phases. So the low voltage B phase was out of spec by 17%. And when we performed excitation current, we saw that the B phase somehow was having an excessive current draw. And the current draw was so excessive that typically you would test for excitation current at 10 kV, but we weren't able to reach that 10 kV value at all. The test set would trip at 5 kV itself because of this excessive current draw. And even when we compared values across all three phases at 5 kV, we saw that the current was very high for the B phase as compared to the A and the C phases. So now we have two tests that we performed that are potentially indicating an issue. And because of the nature of this situation, we recommended that we need to perform some advanced diagnostics. By that, we recommended SFRA testing as an advanced method to diagnose further issues in the transformer winding. Now, unfortunately, we didn't have any baseline results for this transformer, or nor did we have any other similar transformers that had SFRA traces that we can compare it to. So the decision was made to compare phases with each other. So we compared the A phase, B phase, and the C phase, the response of each phase with each other. Now, we performed short circuit tests on that transformer. So here you can see this is the short circuit trace. And I would like to get your attention to the left-hand side of your screen in the low frequency region. You can see the response is flat. And let's look at it a bit closely. once we reviewed the response at the low frequency, we saw that not all the phases were lining up close to each other. You can see that the blue trace is farther apart by about maybe minus zero point 0.5 dB from the red and the green traces. So this was intriguing, and we kind of started to troubleshoot and understand that we already have winding resistance and excitation current that are giving us an indication of a potential issue. And we also performed SFRA short circuit tests, and we found this response. Now, if you review the IEEE guide on SFRA, that is IEEE standard C57.149, it'll state that if your frequency response at less than 30 hertz has a horizontal nature, that response can be compared with winding resistance measurement. And if there is any difference between the phases at such low frequencies, it is recommended that you perform a winding resistance test to confirm what you're seeing. So now our case was a bit in reverse. We already knew that the winding resistance for the B phase was out of specification. And when we performed SFRA testing, we realized that there is an anomaly and there is a mismatch on how the phases should line up. So after having all this information, we also decided to perform more open circuit tests on the high and the low voltage sides of the transformer and compare across phases. So when we reviewed and when we performed the test, we saw several other anomalies as well. And those were involving some loss of some resonance peaks. And we also saw a shift in where the resonances occurred and some unexpected crossovers. So that leads us to the thought process that we can put all the data that we have now in one basket. So we have a winding resistance measurement that said that it was out of spec. Next, you had a excitation current that could not be performed at 10 kV because of excessive current draw and had current traces that were not matching up very well. And then you had short circuit tests that showed some separation between the phases, as well as open circuit tests that showed us other anomalies, including issues with loss of resonance or shifting of resonances, and including unexpected crossovers. So based on that, an aggregate assessment was made on the condition of this transformer and the condition of the windings. So what were the observations? We saw that SFRA testing confirmed our questionable winding resistance measurement. So although we did get a 17% deviation, it was very important to perform another set of tests to come to the common denomination. So we did not just make a unilateral decision of calling the reading as out of spec, because we used other testing techniques to arrive at the same conclusion. As I stated, that we had more than one test that was indicating problems. So what was the final outcome? So it was decided that the transformer will be retired from service after 50 years of operation. So in this case, because of winding resistance measurements, we knew there was an issue, and that probable issue was confirmed by other testing such as excitation current and SFRA to come to a common conclusion that the transformer potentially had issues, and rather than having an unexpected outage and catastrophic transformer failure, it was decided proactively to retire the transformer from service. So these are the kind of decisions that are very important to transformer owners, and where you use several complementary testing techniques to arrive at one conclusion. Now, if you guys want to know more about our sweep frequency response analysis or SFRA testing, we have an upcoming webinar that's scheduled for next month, and I would recommend that you register for that. So now that ends our case study. So let's look at some products that Megger has to offer for winding resistance measurements. We have several of those, and we start with the MTO series, the MTO 210 and the MTO 250 shown here that has a 50 amp capability. Of course, we have the MTO 300 series, and the MWA series has the capability of performing winding resistance and turns ratio at the same time. We just saw the importance of having more than one test confirm an issue with a transformer winding. So the MWS series will allow you to test for turns ratio and winding resistance in the same test set. And of course, for broader substation equipment, including transformers, we have our track series, which will look at winding resistance turns ratio. It will also review the make before break for tap changers. That's another testing solution. So now let's summarize our discussion for today. So we know that based on what we discussed, that winding inductance will determine how quickly or how much time it will take for the resistance measurement to stabilize. And in order to be efficient in that process, we use test current and open circuit voltages for our instruments, and they can help to give us a stable reading and fast core saturation. And it's important to be cognizant of the winding configuration. And you can have, as we saw in our examples, you can have delta windings that can be difficult to make measurements because of the loading from the other untested phases. So in such cases, you can use the dual winding injection, where you are injecting current from the high voltage and the low voltage of the same phase. And this will give you fast core saturation and improve the testing efficiency. And in cases where you do make testing and you do get results that are out of specification, it is important to understand those results, and you have to compare those results with what industry standards recommend and compare them with other complementary tests. As we saw in our last case, where we used more than winding resistance, we used excitation current and SFRA to come to a common conclusion. Remember that winding resistance is a diagnostic tool, and it can be used in several times through the functioning of a transformer. It can be used right at the design stage, in the manufacturing stage for design verification, and it can also be used for commissioning testing while the transformer is new and ready to be installed, or even throughout its service life, where it's tested periodically for maintenance. And winding resistance measurement depends on the design and construction of the transformer, as well as depends on the capability of the test instrument you are using. And then we looked at some more case studies that involved paying attention and being knowledgeable about the winding configuration that you're testing. So we saw different types of techniques we used. And of course, using the right measurement technique can help you get fast and efficient winding resistance testing. With that, I would like to end my case study presentation. It's over to you, Mike.
All right, thanks a lot, Samir, and thank you for joining us for that. That was great. So, as stated before, the presentation portion of the webinar is officially concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or a quote on any Megger product. A copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for our upcoming webinars on our website at us.megger.com/webinars, and register for our next case study and field experience review, sweep frequency response analysis, on August 12th. The presenter will be Volny Naranjo. All right, let's jump into your questions. The first one I have, I'm going to be directing towards Daniel. Daniel, how do you select voltage? Most instruments only select current and voltage is selected by default by the instrument.
Yes, thank you, Michael, and thank you everyone for joining us in this session. So as the person who asked the question said, the voltage is typically defined or selected by the instrument. And that is correct. That's the way the instruments work. So you or the user selects the test current, and based on that, the instrument will adjust the voltage to inject that current. Now, if you remember from Samir's presentation, he mentioned this important factor as it's important to consider when selecting an instrument to perform these tests. I'll give you an example. So if let's say you see an instrument that can tell you that, okay, the capability is 100 amps. Also look at the compliance voltage of the instrument, as is equally important as the current to achieve stable readings as fast as possible. In other words, again, if you have an instrument with 100 amps capability, but a small or low compliance voltage, it won't be of much help as, let's say, an instrument with 50 amps, but with a higher compliance voltage. So yes, the voltage is defined by the instrument, but look at the specs. This is important when selecting an instrument to perform these measurements.
Thank you, Daniel. Dinesh, we have a few distribution transformers with DETC. Do you recommend to exercise these DETC contacts during PMs, or are you aware of any issues by exercising the DETC contact?
Thanks, Michael, and thanks everyone for joining us. Good afternoon to you guys. So it's a very interesting question because this comes up quite a number of times. When you talk about de-energized tap changer, and primarily in US, you would find those on the high voltage side. And because the voltage regulation typically takes place on the low voltage side, de-energized tap changer position could be set at one position for a long period of time. And if the DETC tap has not been moved for a long time, it is recommended, and I believe it is even in the standard as well, that if you have not exercised the DETC contact for preventive maintenance, it is not recommended to move the DETC contact, and you should only test the in-service tap of the DETC tap changer. And when you're doing the commissioning test, yes, it is recommended to exercise and take the measurement on all the 5 taps. But during the preventive maintenance, it is not recommended, because if as I mentioned earlier, if the contact has not been exercised, what happens is that the contacts might be pitted together. There might be some carbon deposit between the contacts, and when you try to do that, you might create more damage to the contact than actually there is. So it is recommended not to do that if it hasn't been moved for a long time.
All right, thank you, Dinesh. Daniel, how do you calculate the winding percent difference?
Okay, there's a couple different formulas to calculate that percentage difference, and these are by standard documentation, right? The standards published by either the IEEE or the CEE. So on the ANSI or the IEEE standard, the formula is you calculate the average of your 3 phases, right? Adding the 3 values together, dividing by 3, and then to calculate each percentage difference is the maximum resistance minus the minimum resistance divided by the average, and then multiply that by 100 to get the percentage. On the CEE standard, you have to also calculate the average value between your 3 phases, and then you can calculate the errors per phase. And notice these are not the percentage difference, these are the errors per phase. So on each phase, you take the value and then you subtract the average for that phase. The percentage difference on this case is the maximum phase error from the 3 that you calculated before, divided by the average, and then multiply it by 100. But a couple different ways depending on the standard you're using to analyze your results. This is for sure, obviously, the formulas, there's a couple different factors involved. In our case, PowerDB, you just have to select the standard to be used, and the software will calculate the error for you.
All right, thank you, Daniel. Dinesh, what parameters are used to define a stable reading?
Again, that these are some very good questions that are being asked by the attendees. When it comes to the parameter that you use to define whether the readings are stable, typically what we use, and when I say we, it's about any equipment manufacturer. We use that the reading needs to be 99% stable for a period of about a minute. In other words, the reading should not deviate by more than plus minus 1% from its previous reading, and it should stay within the tolerance for a minute. And when that happens, that's when we call that as a stable reading, and the test set has the option for saving the results automatically based upon that criteria. I do want to bring one point in regards to this one, that whenever you're testing a low voltage winding, which is a delta configuration, what I would recommend is that because in the delta configuration, as Samir stated, that there is a current flowing in the other two legs of the delta winding, sometimes the readings might appear that they have stabilized, but in reality, that's the level 1 of stabilization, and it would seem like it's stable, and then it would fluctuate again, and then there would come a second round of stabilization when all the three phases have been neutralized when it comes to the inductance, and that's when the windings or the readings are truly stabilized. So when you're testing low voltage winding delta configuration windings, I highly recommend to keep a close eye on this criteria, because you may have to test the first reading manually to make sure that those are truly stable reading, and then from that point onward you can use the automation available in the software tools, but be mindful of the low voltage delta winding testing.
Thank you. Samir, in what standard can we find the 2% resistance tolerance between phases?
So, several industry standards discuss the 2% tolerance across winding resistances. So, some references I would recommend the attendees to review would be the IEEE standard C57.152, which is the diagnostic guide for transformer testing. In addition, you have the IEEE C57.12.90, which is the standard test code for transformer testing. And you can also review the NETA standards, which are the acceptance testing specification, that's the ATS, and the maintenance testing specification. So they will have more discussions on the 2% variation between windings. So those are good references I would recommend the attendees to review.
Thank you. Next question is going to be for Daniel. Is there any specific method to use when testing a transformer with an Oltc?
Okay, great question. And I wouldn't say a specific method, but the recommendation is to use the automation that is offered with both instruments and the combination of the instrument and PowerDB. Dinesh mentioned a little bit of that. So when you have a set of windings or you have an Oltc, right? The Oltc is designed to change position when the transformer is energized. So certainly, I mean, when you're measuring winding resistance, as Amir mentioned, you're using up to 15% of rated current, so relatively low, right? So you can start by injecting current, right? Typically, you start on either extreme of the tap changer, either the lowest or the highest position. So you start the injection, and obviously, you know, we will take some time to get a stable reading. Once you have that first measurement, you don't have to de-energize or discharge that energy, right? You can actually switch to or change the position of the tap changer to the next, and the reading will be much faster. I mean, the current will keep flowing through the winding, and again, you don't have to wait for that to be stable. So you can continue doing so through all positions of the tap changer. In certain configurations, for example, if that set of winding is connected in star configuration or a Y, you actually can measure two phases at the same time in a way that you will go in one go, right? Going from the, let's say, the lowest to the highest in one exercise of the tap changer, and then you switch to the third phase, and then the software will actually go back to the lowest position of the tap changer. So you only exercise the tap changer in the full or the all positions twice, right? The first one to measure two phases, and the second one to measure the remaining phase. So again, rather than specific, it's just a recommendation. It will actually save you a lot of time, right? If we take the standard configuration here in North America, right, a low tap changer with 33 positions, so you have 99 measurements to take. But again, using this feature, this help from the software and the unit, you can save a lot of time while taking these measurements.
Thank you, Daniel. Samir, next question was for you. What is the importance of demagnetization?
That's an excellent question. And because of the nature of this presentation, we couldn't concentrate a lot on demagnetization because we had a lot of case studies. But demagnetization is a really important practice that needs to be performed after you complete winding resistance measurements. First, that's because you are saturating the transformer core with a direct current and with direct voltage. So that's not typically the normal state of a transformer when it's in operation. We used alternating quantities. So if you do not demagnetize, what will happen is when you're performing other consequent testing, let's say the best example is excitation current. So when you are measuring or testing for excitation current, you will get values that will be erroneous because now you are not magnetizing the transformer from the proper starting point, and you already have some remnants in the transformer core, and this will affect your readings. In addition, if you do not demagnetize the transformer, and if you try to re-energize, say you've completed your testing and you forgot to demagnetize, so in when the transformer is being re-energized, the differential protection schemes might see that magnetized core to absorb more current. And that might be seen by these differential protection schemes as a fault, and then you would have a nuisance trip. So it's always recommended that you perform demagnetization after winding resistance. So that's a really good question. And if you review industry standards such as C57-152, they do mention that caveat that understanding the previous magnetic status of the transformer is really important before you begin testing. And from a testing sequence, if you can perform all your tests before winding resistance, that's better, because then after you perform your resistance measurements, you can completely demagnetize the core, and then you're ready to move forward with your next step.
Thanks, Samir. Dinesh, when should the dual winding injection be used?
So Samir covered a couple of case studies where he talked about dual injection. And basically, the idea is for us to saturate the core faster by having more number of ampere turns, which would result in more flux. More flux would result in faster core saturation. Now, this dual injection obviously is a great method to speed up the test. One of the places where you may want to be careful in using dual injection would be when the turns ratio of a transformer is greater than 10 or 15. You may want to stick to single injection method. And the reason for that is that when there is a big difference between the number of turns of primary and secondary, the rated current of primary and secondary would be different, or there would be a big difference. And as Samir mentioned, that you cannot exceed more than 15% of the rated current of the winding under test. And if you're testing both high voltage winding and low voltage winding together in series, you are limited by the maximum current you can inject with the rating of the high voltage winding. And if the ratio is greater, then the amount of current that you can select may not be enough for the low voltage winding, because the high voltage winding would have lower current rating. And because it's in series, you cannot exceed more than 15%. So the amount of current that you're injecting may not be sufficient for low voltage winding. And it may take even longer time to stabilize because you're not putting enough current into the circuit. So if your turns ratio of the transformer is greater than 10 or 15, you may want to stick to single injection. But if it is lower than that, then dual injection is highly recommended because it will speed up your testing.
All right, thank you, Dinesh. Daniel, can I use a low resistance meter to perform this measurement on small transformers?
Okay, very, very important question. And the short answer is no, is not recommended. We at Megger get that question asked a lot because we offer a wide range of low resistance zone meters. But, and I think Samir briefly covered that in the beginning. Again, the focus of the webinar was case studies, not so much on the theory, but remember that when you are performing this, the inductance of the transformer plays a big part, right? So when you are injecting the current to take the measurement, you're pretty much storing energy, right? And that has to do obviously with the time that you have to wait for the current to be stable so you can take an accurate measurement. Once the measurement is complete, that energy has to be discharged, right, to be safe for the user to swap connections if needed, or to just simply disconnect when finished. So again, the important part here is that discharge process. So a DLRO is not designed to do so. So the DLRO it won't have the proper circuitry to discharge that energy. So certain models, right, will have what is called an inductive mode, and I would say that will be reserved for very, very small inductive loads, either motors or transformers. But I would advise to keep these measurements for a proper transformer or proper instruments like the ones that Samir showed at the end of the presentation.
All right, thank you. Dinesh, do you recommend performing three-phase winding resistance measurements?
That again is a question that would require some explanation. So allow me to explain that. So there are various different methods you can use to perform winding resistance. You can use a method which we call a single phase current injection method, where you test A phase, then you move the leads to B phase, then test B phase, and then move the leads to C phase and finish the test with the C phase. That's your single phase traditional per phase measurement. Then we have a three-phase instrument where all the leads come from the instrument connected to all the bushings, but it performs the test one phase at a time. So it would energize A phase, get the measurement, discharge it, and then move the current source to B phase because all the leads are already connected, and then it would sequentially move to C phase, which is what we call as three-phase testing, but on a per phase basis. Then there is another method which we call as true three-phase testing, where you actually have three current sources and you apply all the three current at the same time, and then you measure the winding resistance of all the three phases at the same time. Now, when you do that, there is obviously a distinct advantage that you have more current, which means more flux, and you would get your results faster with a true three-phase winding resistance measurement. But having said that, there are some disadvantages with that as well. One of the disadvantages that you can only use three-phase injection for a Y winding configuration. You cannot use it for delta configuration because of the delta loop that's there. It will create instability in the current injection, and it's not recommended for a delta winding configuration. The second difference is that when you do the three-phase injection or true three-phase measurement with a three-phase source on a Y winding, the neutral bushing would have 3 I current flowing in it, whereas the current measured by the current source is only I. So that's the reason why your readings with a per phase testing and three-phase testing may not be the same, because the actual current flowing is 3I, whereas the recording by the instrument is only I. And then the other things are like when you do the three-phase injection, you cannot do dual injection method, and you cannot test break before make functionality of Oltc. So there are some advantages with the three-phase testing, but then it has a very limited application, given you can only test Y winding, you cannot test delta, the readings would be different, you cannot do dual winding injection, and you cannot check break before make functionality of the tap changer. So you just have to decide whether it is fit for your application, but per phase testing is considered to be the most efficient and most accurate one.
Thank you, Dinesh. Additionally, while I have you, the next question will be for you. From experience, resistance measurements from tap 1 to 33 and 33 to 1 on Oltc gives a slightly different result. Do you have any experience with this?
Again, that question, I can easily tell the gentleman who asked that question have had experience in the field, and that is a true statement, because when you talk about Oltc, typically there is a reversing switch, or you might have a preventive auto, and depending upon from which direction you are coming, your readings may differ slightly. But remember, what is the goal of the 33 tap testing that you're doing? Either you go from 1 to 33 or 33 to 1. The idea is that you want to make sure that the reading is not changing from your previous measurement. So as long as you're consistent in the way you are doing the testing, let's say 5 years back I did the testing and I went from 1 to 33. I want to make sure that I follow the same path maybe when I do the test this year. And the other thing is that when you're testing the Oltc, you're trying to compare the results between A phase, B phase, and C phase, because temperature is not a determining factor anymore, because the temperature is same for all the three windings. And when you do that, you're trying to compare A, B, and C. And when you plot the 33 tap curve, if there is any one reading that stands out, would be very visible in the V graph that you typically get. So I do understand from where the question is coming from, whether you go high to low or low to raise to low or low to raise on a LTC. But for all practical purposes and trending purposes, you would not see a big difference. And the key thing here is that you need to be consistent. Whichever way you are doing the testing, you need to repeat the same method year after year.
Thank you. Samir, what is the effective demagnetization current? From my experience, it's 2 to 3 times the magnetizing current. Could you please advise?
Yes, of course. It's a good question on how you would effectively conclude a winding resistance measurement. That's by doing demagnetization. Now, if you review industry standards, the key aspect there that they mention is the magnitude of your current that you use to demagnetize the core should be the same that you use to measure the winding resistance in the first place. So if you used 10 amps to measure the resistance of a transformer winding. In order to demagnetize, you should use that same magnitude. And the other important aspect of demagnetization is that you have to vary the polarity and the magnitude of this demagnetization current. So if you look at demagnetization techniques, you would have one of them will involve changing the magnitude and polarity. So you start off with a negative 10 amp current, then you change the polarity to positive 6 amps. So you change the polarity and the magnitude both, such that all the magnetic domains in your transformer core become randomly aligned as they were when the transformer was de-energized. So that's the key of ensuring that the transformer core does not have any more magnetization left. So the key would be selecting the same magnitude of test current for demagnetization, and by varying the polarity and the magnitude of that current. So you progressively decrease the amount of current. So you start off with 10 amps, and as you change the polarity of the current, you also change the magnitude. So from 10, you would go to say -6, then you would go to +3.5, and then you would go down to -2. So that's how you would see that change in your demagnetization procedure. And most of these procedures are automated. So if you look at any of our MTO instruments, it will recommend a test current based on how much you used for making winding resistance measurement in the first place. And then it will automatically vary the magnitude and the polarity of that demagnetization current.
All right, thank you, Samir. Dinesh, if you do not de-energize electrical charges after injection, how does that affect the next testing?
I believe in this question, by the word de-energize, they are meaning discharge. If going back to school days, you always remember that that capacitor stores the energy in the form of electrical energy, and inductor would store the energy in the form of magnetic energy. And let's say if you are testing a winding, you are basically testing a coil which has resistance and inductance. And when you apply a DC current to that, you are inductor is basically storing that energy inside that inductor. And if you were to stop the test and not discharge the energy, that energy is trapped in the inductor. And when you try to take the leads off at the end of the test, what would happen is that that energy has to dissipate somewhere. And when you break the circuit, when you take the leads off, that energy would manifest itself in the form of a arc, which could be lethal to not only the person who is doing the testing, but also to the instrument, to the asset under test. So it's not a good situation to be in. So it's highly recommended to de-energize or discharge the energy stored, so that way you can safely disconnect the leads. And then the other thing is that you are not leaving the core with any kind of residual magnetism, because that would affect later down the road when you're going to perform some other test. So I hope that answers that question, because when you use the word de-energize, I always think of the word discharge when you talk about inductors.
All right, thank you, Dinesh. It looks like that's all the time we have for questions today. We apologize if we didn't get to your question live, but we will be following up with you offline after the webinar. But I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. A copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. But once again, I'd like to thank you all for attending, and I hope you all have a great week.